Oh. Okay. So, which cloud is fog most like?
Stratus.
It is most like a stratus cloud.
Yeah.
If I had some candy, I'd throw it at you.
Paying attention.
Okay, so
Oh, 1 in 11 guess.
so basically, when you see fog, that's basically suspended little liquid particles. And have you ever done this? Like if you're in a fog, actually look at those little liquid particles falling. I think I might have said this the other day. We're going to call it terminal velocity here in actually part 5. Like how fast something falls, you know, and we usually think that it's supposed to accelerate at 9.8 meters per second every second it falls. Have you ever heard the acceleration due to gravity? Things are supposed to go faster and faster, okay, because of gravity. But kind of depends upon the physics of the object, okay? It will actually hit a fastest speed it's going to fall. It's terminal velocity. So little particles fall slower than big particles.
I disagree with that. Because who was it, Galileo?
Galileo.
Said objects the same size or mass.
Right. They have the same, they did not hit their terminal velocity.
Okay.
But it is possible that you will stop accelerating because of the physics of your object. It won't go faster and faster because of winds, it's air brake. Yep, look it up, terminal velocity.
Okay.
But he didn't hit the terminal velocity of
And in space, there is no terminal velocity.
That's
Everything
true.
falls at the same
So
It's an
terminal
air
velocity
resistance thing.
Terminal velocity goes against Galileo's findings.
Yeah, if he was up against different physics of different objects, and I think he specifically took 2 objects that had the same, very similar dynamics as they fell, and they would fall at the same rate.
Okay.
So we're on the same page. So there's 4 types of fog, but what they have in common is they're most like a stratus cloud. Radiation fog, I kind of tease, it's the one that kids get up in the morning and they're hoping that there's fog.
Fog delay.
Yeah. Fog delay, yeah, exactly. That's radiation fog. And the reason they call it radiation fog is basically they're counting, those little kids are counting on the Earth radiating its heat. Basically, its heat is going to peter out. So basically, it'll create what we call a temperature inversion. So it'll have this nice warm air, okay, whatever. You know, it was sunny the day before and it kind of gives its heat off, blows its heat off. And then it will be nice and cold, okay? That's a temperature inversion. It's cold and warm air above it. So if it gets cold enough, we can reach the dew point temperature and kind of nice, gentle winds. Okay, clear, no, we don't want any clouds, we want radiation fog. So that's one type of fog. Then there's this advection fog. Okay, now, advect is actually a verb. If air advects, check this out. It goes opposite what we've been talking. We've been talking about air going up, okay? If air advects, it moves horizontally, not vertically, okay? So advection fog, air is moving horizontally. And so it works well with coastal regions. It's like if you've watched those scary movies and the fog moves in, okay? That's the scary fog.
Like the mist.
Yeah, like the mist. Yeah. Why don't these people run? You know, I'm just like, okay.
Then they trip when they run.
Yeah.
They trip and they just somehow can't get back up.
Yeah, so they have to
Like-
crawl, they just can't get up.
Duh.
I just like the Family Guy when Peter Griffin gets hit in the leg.
Oh.
I haven't seen
Oh,
that
man.
yet, so.
He did that for probably 10 minutes of the episode.
Yeah, it was a long time.
The third kind, to me, reminds me of orographic lifting we talked about tonight. Let me see if I can pull up my pen. Okay. Orographic lifting. Hopefully, to me, if you remember mountains and orographic lifting, it'll work real well for you. So basically, this is the sort of fog that's formed by maybe even a prevailing wind has moved moist air, pushed it against a hill, okay, and that's going up, okay. So upslope fog. It's possible that if you have in your car gone up a mountain range, okay, it's possible that you hit some layers of fog. And so, evaporation fog. This is what actually, evaporation fog is the thing that fills your bathroom in the morning. Okay, evaporation fog is depending on not cooling necessarily, but basically taking water vapor and somehow getting water vapor into the air. Evaporation fog. There's actually three names for this sort of fog: evaporation fog, steam fog, and frontal fog. Here's one. Have you ever gone down, to me, the Skunk River? I kind of cross it on the way here from Burlington to, okay, and especially in the mornings, you kind of see that misty fog, okay, on the river, the nice calm river, or it could be a pond or whatever. So the reason it's called evaporation fog is basically that river or that pond, it's still nice and toasty, and so it's got its fair share of basically evaporating liquid water. Okay, so it's nice and saturated above that river or that pond. Okay. And this, of course, in our shower, I think we talked about this before, basically you are injecting water vapor into your room, okay, which can go ahead and saturate your air, so you get fog there. Yeah. This is the sort of fog, I think I might have told you if you go to Adventureland, they have, their pavement for some reason is black asphalt. I don't know if they've changed it now. But you could have a nice sunny day, okay, and then have kind of one of these quick showers come in. Hot pavement shower, okay. Basically, you get that kind of steam coming up off your pavement. Okay, so that's frontal
I
fog.
get it on my head a lot.
You get it on your head?
I do.
Oh, frontal fog, oh. Yeah, I can see
I
that.
get really warm working out or whatever.
It
Go
uses-
outside and just.
Yeah. Football games. After the game, takes off the helmet, boom, everywhere. Steam.
Oh my gosh, you're creating your own frontal fog.
Yeah.
Sunglasses.
Oh yeah, condensation on sunglasses maybe.
Yeah.
Cold from a hot to a cold room.
Yeah, yeah. Condensation on your sunglasses, yep. Those are all great examples.
So I have to ask, does it come off your head because you're bald?
No,
Wow.
it
I'm really lost because I've never seen it happen to anybody, so.
You never have?
No.
You've never
Oh,
been
wow.
like, you've never seen like on the sideline of the football game.
What's a
Guy-
football game?
He's playing with you.
Okay, so
He's trolling.
they come off the field, right?
Yeah.
It's a cold day.
I guess it
It's a
has
They've
to.
cold
been-
day.
They've been running out there, they've been sweating,
How cold?
real cold, it's snowing.
You're
Snowing at
I
Lambeau.
legit have not seen that ever.
Take the helmet off, just steam coming everywhere.
I was,
It's crazy.
I was a
Painting the picture.
kicker, so I
Yeah, you
never
didn't know.
experienced
Yeah,
it
you don't know
myself.
what that is.
You didn't sweat, did you?
No, I just went out there, did,
Yeah,
my-
well,
did my
on
job
purpose,
and
I
walked
went
back.
out, kicked, and walked back. That's all you gotta do.
That's fun.
Oh, okay. So 4 ways you could get fog, and that's one of them. So this map is talking about the 4 different ways to get fog. We're most likely to get radiation fog, probably just radiation fog. We don't have any mountains to get upslope fog. We don't have any large bodies of water to get advection fog. But I guess we could get that frontal steam fog all the time.
I've heard that, maybe this is coincidence, but when you have fog,
I can't take you seriously. You're eating fish. Go ahead. When you have fog,
when you have fog, if you count 100 days, exactly, on that 100th day, you'll have fog again.
That's some Farmer's Almanac stuff there.
yeah.
I trust that book.
It's
Very
remarkably
extreme.
accurate.
Yeah.
And I've counted it once, and it actually happened.
That's bizarre.
It's Farmer's Almanac
Okay.
stuff, man.
I live like
It's
10
And then 100 days later, you have
Every
more
day's
fog.
fog.
Yeah, yeah, I
Yeah.
live 10 feet off the Mississippi River. Like yeah.
Every day's
And
fog.
every day is foggy.
So
So
it
that-
works for him.
Yeah, no, it definitely works for me. Yeah, no, I live right like
That would be neat.
Your
No,
backyard's
I've
my
known that
backyard
before.
is the river.
Yeah.
That's
Sure as
that's
shit.
strange.
I'll have to, that does sound like a farmer's almanac thing. Yeah. Interesting. I don't know. I hadn't heard that.
Naughty.
Okay.
I think we should have tacos delivered to this guy.
No, I don't think it's going to happen.
I don't even remember what you said.
I think we should have tacos.
So we talked about if you guys have been doing your weather logs, one of the things you're recording is the dew point temperature. It's always a temperature beneath the current temperature at which you're going to go ahead and the air will be saturated. And if that dew point temperature is colder than freezing, guess what? It won't be dew, it will be frost, right? So sometimes, I don't know if you've seen this phenomenon, but we said that clouds have a warming effect, kind of, right? Clouds have, at nighttime, clouds have a warming effect. They kind of trap that outgoing terrestrial radiation. But trees also have a warming effect. So if you're trying to get dew or frost to form, the fact that there's a tree here basically kind of keeps you warmer than usual. So honestly, trees inhibit the formation of frost and dew. Cars, on the other hand, are great or frost magnets, aren't they? Yeah, if it's going to frost, it's going to frost on your car. Okay, so because they cool down very quickly. All right. So when we talked about, we said that there's this possibility from a vapor to go straight to a solid, okay? And that's what happens with frost. And we would actually call that deposition. There's the word for it. It's like 680 units of energy are released during deposition. Dew point temperatures, those have been what you've been recording. Like I said, that's the temperature it needs in order for condensation to occur. So this link actually is going to take us out to what the conditions are right now. So we'll just kind of take a look at the current temperature and what the dew point temperature is. See how close we are. See if you're going to have to scrape frost off of our windows in the morning. And I'm using the Weather Channel. I like the Weather Channel. I like AccuWeather too. So this is supposed to make us feel better. It's 8 degrees, right? And it's clear. The details will give us how far we need to go in order to reach 100% relative humidity. So we're at 8. We need to go down 9 degrees in order for it to frost. So like I have a student in my other class pointed out, so I guess we just need to look at our overnight low. And if it's not going to be cooler than -1, we shouldn't have to worry about frost, should we? Okay, so that's kind of how that works. Very good. Okay, so we talked about cloud condensation nuclei, that little piece of dirt that's going to get the party started, whether it's hygroscopic, it loves water, or hydrophobic, it hates water, it'll get the party started. Well, this is kind of showing you kind of relative sizes of liquid particles in the cloud. So those cloud condensation nuclei are the little dots. That's about how big that the party started gets going first. It's not going to be probably until next week we're going to kind of talk about how that little liquid particle gets larger. But we are going to talk about snow here in a minute. Okay, so within that cloud, larger than the initial cloud condensation nuclei could cause, we have some relatively large droplets, okay, and even larger droplets. And if you're like me, did you miss that big droplet at the bottom? So kind of drawn to scale. This actually is typically what will fall from a cloud. Okay, this is what it starts. You kind of see some intermediate sizes, and this is what will fall from a cloud. Okay, so that's just to kind of get you thinking. We need to talk about that growth process. So a player in that growth process is a phenomenon of water, liquid water, called supercooled water. Anytime you hear the word super in physical science, it means it basically is a condition above, or in this case, below which it should be. Supercooled water is liquid at a temperature cooler than it ought to be a liquid. That's what it is, supercooled water. So this should be a video, and maybe you can relate to this. So what this is saying is up in the upper troposphere, where it's -40, -60, water's still liquid. Supercooled water. Supercooled water. Okay. So one of the things we're hoping, if you fly much, and I don't fly much at all, but they want to put some solution on their wings as a de-icer, right? Because if an airplane is flying through liquid water droplets that are super cooled, it's disturbing those cute little liquid water droplets that are super cooled. And it will, if they don't treat their wings, basically make like a solid mass on their wings.
Yeah, and then they'll crash.
And then they'll crash. Yeah, that's not, yes. So the thing about supercooled water is this, that it actually, well, not supercooled water. We're kind of stepping away from supercooled water. I want to kind of talk you a little bit through something. It's a French word called the Bergeron process.
Tom Bergeron?
Not that I know of. But maybe it's related. But the Bergeron process is basically how you make snow. Snowflakes up in clouds. And it counts on this fact down here. So we have a couple of columns. Here we have basically how is the cloud going to be saturated with regard to liquid water. Okay, just say it's saturated. Over here we have, what about ice? What about your snowflake? We'll see how at conditions that are only saturated with liquid water, it's what we call super saturated with solid water. This is your snowflake, this is your liquid water. This is your brain, this is your brain on Earth. Okay? So what we're gonna see in the slide here in a minute is basically solid water, ice crystals, they will grow and your liquid water will just kind of supply the moisture for that. Bergeron process counts on this. Okay, so here we go. Well, I guess it's coming up. So on the slide here, on the figure, I think it's the next slide, what you're going to see is an ice crystal, solid water, falling through basically supercooled liquid water. Okay? Now, the ice crystal is in a situation where it's super saturated. So the ice crystal is going to grow. And your supercooled liquid water is just going to go ahead and kind of keep shrinking, providing water vapor for that ice crystal to grow. Okay? So again, another super. Okay, we had super cooled, right? Too cool, then it should be a solid, but it's a liquid. Super saturated, it should not be above 100%, yeah, but it is. Okay. So here we go. And in the past, I don't know what I'll do for this semester's test, but usually I like the word Bergeron. Has no relation to Tom Bergeron, but to describe kind of what this slide is. It's the formation of see that cute little snowflake? It's not evil, it's cute, okay? The free water vapor you kind of see is the red with the white, kind of like Mickey Mouse, that's water vapor. And the blue, like it says, is supercooled liquid water. Okay, so notice the snowflake getting larger, that evil snowflake, right? And what's happening to the supercooled liquid water droplets? They're getting smaller. They're getting smaller. They're actually providing some of those supercooled liquid water droplets are evaporating into, go ahead and saturate that. Keep that nice and saturated, super saturated for the ice. Okay, and then of course the next one kind of just says the snowflake's even larger. It's got to be such a delicate process up there, you know? That's called the Bergeron process. So you kind of saw from those three frames, you know, the first one, the middle one, the last one was with regard to time, the latest one. You saw it grow, and that's kind of what it does. Not only that, but actually you can have snowflakes kind of get larger, kind of combine via a process we call accretion. So the one thing also I want to get to tonight is this idea of stuff that starts out as snow may not fall to the earth as snow. Precipitation, whether it falls as snow, rain, freezing rain, or sleet, actually has to do with the temperature it runs into as it falls from the cloud. Not so surprising. So one of the things that might cheer you up is on these, kind of spring or fall. I don't know about summer, but what we get as rain really started out as snow. Next week I want to talk more about the rain collision coalescence process for rain. But I want to just focus on the Bergeron process now. These would be cold clouds. Okay, so cold clouds basically snow will fall from the base of cold clouds. You see the snow falling, okay? And all this is saying is if it hits a pocket, so now you have to switch from Fahrenheit to Celsius, but if it not hits a pocket, I guess I should say, if basically as it falls, it melts, it's going to stay melted if the temperatures continue to be warmer than 0 degrees Celsius. So over here, what your author's done is this would be, the blue is freezing, the pink is warmer than, so this would be liquid, so this would be solid liquid. Okay, so it starts as snow, we get it as rain. So here's the other one. It starts as snow, we get it as snow, right? It stays cool enough to go ahead and it won't melt as it gets closer to the Earth's surface. Well, then we get our temperature inversions. See the kink? That is a temperature inversion. Okay, what we're used to as we go up in elevation is as you go up in elevation, it should get colder. So this right here is normal up there. Okay, on the top part is normal. The bottom part is what we call a temperature inversion. Normal, because you go up, it gets cooler. Okay, this is an inversion, because as you go up, okay, it gets warmer. And it has consequences. If that kink will basically go into the melting and then up to the cooling, okay? Basically you have snow, melting, and then refreezing. And how deep that temperature inversion is will either give you sleet like this, or the next slide I'm going to show you, you're going to see the temperature inversion is more shallow. It will give you freezing rain. Okay, so this is sleet.
What about hail?
Hail comes from cumulonimbus clouds. Hail comes from basically an unstable situation. Hail's awesome because it can be different sizes depending upon the updraft and it going up. Basically, a little grapple goes up, it comes down, it goes up, it comes down, it goes up. Hail usually looks kind of like an onion sort of thing. So it's a trip around. So hail, we're not talking about hail here, but we will.
I think you're the first person that's ever
I'm glad
said
you
hail
asked.
is awesome.
What's
I
that?
think you're the first person that ever says hail is awesome.
Yeah. Well, from a
Must be working
scientific
in the
point of view,
garage.
it's awesome. Yeah. As long as if it damages your car, you get your car fixed, I guess.
If you have insurance.
Yeah.
What's that?
If you have the proper insurance.
Yeah. No. Oh no. So
And my car definitely has insurance.
good. So can you see the difference between those two temperature inversions? This one's shallower. So I know it says glaze, but I would call that freezing rain.
That's the same thing.
Yeah, I think so.
It's just a fancy way of putting it.
Yeah, same thing. Have you ever heard like the freezing rain on contact sort of thing? Cool. Okay, so that's how far I wanted to get tonight. Because I kind of want to give a break between our snow clouds with the Bergeron process. I want to give a clear break. And when we come back next week, we're going to pick up with actually not the Bergeron process, but the collision coalescence process within worm clouds. Okay, so no chapter assignment will be due next week.
Not even chapter 4?
Chapter 4 will be due next week. Thank you.
Chapter
Yes.
4 is due next